So we'd like to introduce the concept of the bias-variance trade-off or the approximation generalization trade-off. And we're going to do it in the pre-lecture by looking through an example. Later on in the post-lecture, we'll be going over the mathematical details and the notation to help make it more exact. But for now, let's take a quick example. Let's say we're trying to estimate a univariate function, meaning a function of just one variable. Here, we're just going to review the target function on a particular part of the domain between -1 and 1, so mapped to some real number. And we're going to say that we know the target function is actually the sine function. Okay? Of course, in learning, we are trying to learn the target function. We never get to see it, but just humor us for a while and let's see how far we can get with understanding the bias-variance trade-off, looking at the target function with full disclosure. Great, so now we want to learn the target function. Well, we need a data set, right? Okay, let's give you a data set. We're only going to give you a data set of size 2, just to help illustrate the bias-variance trade-off. And we're going to restrict you to comparing two different specific models for learning. As we're trying to predict a univariate function, we'll just restrict ourselves to different order polynomials. Let's take a look at the first one. Well, our hypothesis set here is restricted to h0, which means just an intercept, right? Just theta 0, which would be a straight line going across the function, right? Regardless of the value of x. Well, that doesn't look pretty good, right? Because obviously we can see a straight line doesn't seem to approximate this function well at all. How about the second hypothesis class? Well, this looks a little better. It looks a lot better than the constant function. Here we get a line that has a slope as well as an intercept. So that looks like it's going to approximate better, right? So our question is, which one of these cases is going to be better? H0 or H1? Well, the problem here is we need to clarify what we mean by better. Better for what? Better for learning? Better for approximation? What do we mean? Well, the first thing we can ask ourselves is which one of these two hypothesis sets best can approximate the target function. Here we get to use the full power of the model to pick whatever hypothesis we want to represent the actual target function. So we're not going to hide the target function here. We're just going to give the target function outright and ask what's the best hypothesis that can be returned for each of these two models. As you can see here, on the left-hand side, we will pick the constant of 0 because that's the one that's going to minimize the squared error. If we pick any other line, for example this one here, the squared error on this side is going to kill us. So we have to move up and down on this line and we're going to converge on 0. So indeed, this really is the best line that we can do because it's going to minimize the squared error here and here. What about for h1? Well, we can try many different types of lines and see how far we get, but the one that's going to minimize our squared error is the one that we've shown in red here. I'm going to trace it again with blue, because that's going to minimize all of these places where the squared error might get large. And indeed, we can verify the cost on any expected test value that we might get. Indeed, as we would expect, the test cost for the constant model is significantly higher than the one for the straight line. So that was approximation, a problem that we might have in statistics when we're given a process and we need to model it in some way. But this is a machine learning course and we're not interested in approximation, we're interested in learning. Let's look now at what happens in the learning case. Let's focus first on the figure on the right. What we're doing in learning is taking a specific data set that we acquire from the target function and observe. So for example, here on this chart, Let's pretend we can't see the target function, but we've sampled 2 points from it, namely this point and this point, right? If we just get to observe those 2 points, I think we'd all agree that the best possible line that we would draw to minimize mean squared error would be the red line that connects both of the points together. This obviously has a mean squared error of 0, so it's the best possible line we can get for the data set that we've acquired. But of course, this line is dataset dependent. If we picked another 2 points, say these two over here, we might draw a different line. So the hypothesis depends very much on the dataset that we draw. Let's turn our attention to the left-hand side. Here we might sample 2 points, the same 2 points as in the first case. And the best hypothesis we could come up with was probably going to be the average of these two y values, which leads us to the green line that's already drawn there. Again, we can sample different points and get out a different value. In both cases, we can see that the hypothesis is going to vary quite a bit, depending on which 2 points we're going to sample for our data set. So let's go ahead and see how this pans out. Let's take a look at H0 on the left-hand side here. Here we've run a simulation, and we've picked 2 data points, just like before. For example, here and here, and drawn a particular hypothesis. But we're going to repeat this process many, many times, and you can see all of the different lines that are drawn from this. As we can see, the lines in the middle happen to be more dense because it's not so easy to draw lines close to the top, right, or the bottom. For example, to draw a line towards the bottom, we would have to choose 2 points that are fairly close to the bottom so that the average comes out close to the lines that you see here. Going ahead, we can draw the average hypothesis that we might result. We're going to call that H bar. This H bar is really exactly like it sounds. We're going to just average all of the different hypotheses that we got out over all of the different samples. And you can see it comes very close to the optimum hypothesis of y equals 0 that we saw when we revealed the entire target function in the approximation task that we saw at the beginning of this section. We can also measure the variance of the hypothesis by taking any one x value and calculating the standard deviation of all the points. Say we take this x value here, then we just average all of these different points, which would be the values of y given that value of x. Here we're showing the standard deviation, which denotes the variance. So how does this look for the H1 case? Let's take a look. Here on the right-hand side, we've taken the same exact set of points that are responsible for all of the hypotheses in the H0 case. But instead, now we've drawn a line that connects the 2 dots together because that's going to minimize the mean squared error for 2 points. And you can start to see what might be the problem here. Just as before, we can see that the average hypothesis, by averaging out all of these lines, might be close to the optimum. Indeed, it is so. The average hypothesis here is really close to what we saw in the approximation case as well. What really gets us is the variance. You can see this by taking again any particular point, say the same point, and then drawing all the dots for where those lines would end up for the specific hypothesis that were chosen. When we take this series and calculate the standard deviation, we can understand the variance here. Okay, so we can see H1 doesn't look so great, but how bad is H1 compared to H0? Is it really going to be the case that the variation in the expected data set will cause the error due to variance to really kill us? Let's take a look. A couple slides back, we saw that the yellow region in H0 was larger than the one in H1. The size of that area is proportional to the expected amount of error that we would get on any test point. Here we can see that the bias is greater in H0 than H1. But how about the variance? In the first model, H0, we see that we have some error due to variance, which is proportional to the size of the gray area. What about for H1? You can see the area is a lot larger. In fact, it's fairly large. We're getting a result that's close to 1.7. In fact, when we add up both sources of mean squared error, we can see that in the case of H0, we're going to get a smaller amount, something about 0.75, and in the case of H1, about 2. So now you know, when you're faced with a data set of a very small size, such as 2 points, a constant is a better choice for learning the sine function than a straight line, even though it's clear that a higher order polynomial, such as a quadratic or a cubic polynomial, is better for approximating the actual target function of the sine. So we've learned a very valuable lesson that we're going to edify a bit more in the post-lecture, which means that when we're trying to apply machine learning, we really have to think about what data resources we have available in terms of both the quality and quantity. We're going to use these data resources to decide how much model complexity we can afford. Even though we might know something about the target and how complex it might be, it's often the case that the dataset scale and its provenance, that is, whether it's noisy or is pure, will help us judge what type of model we should be fitting to the data.